Imagine, just for a second, an object only about the size of a city. But it possesses a magnetic field so unbelievably powerful that it makes our entire planet's magnetic shield look completely insignificant. Welcome to this explainer. Today, we're exploring a cosmic phenomenon that honestly sounds like it was ripped straight out of a science fiction novel. But it's very, very real. It's called a magnetar, and it might just be one of the most extreme, mysterious, and awe-inspiring forces nature has ever created.
To really understand a magnetar, we first have to wrap our heads around an absolutely staggering shift in scale. We're looking at an object with a diameter of only a few tens of kilometers, so roughly the size of a large, dense earthly city. But, and this is a huge but, it contains a mass that is actually greater than our entire sun. This is an extreme reality of our cosmos. It's an environment so unbelievably dense that the normal rules of matter as we know them just completely break down.
But, it's not just their size and mass that make them mind-bending. It all comes down to this single, staggering metric: trillions. With a T. These objects possess a magnetic field that can be trillions of times stronger than Earth's. Now, Earth's magnetic field is already vital to us, right? It deflects charged solar particles and basically makes life possible. But a magnetar takes this concept and amplifies it by trillions, creating a magnetic environment so intense it honestly defies human imagination.
So, that naturally brings us to a pretty major question. We know they're small, we know they're astronomically dense, and their magnetic fields are beyond powerful. But what exactly is this cosmic monster, and how on Earth, or rather, how in space, is it actually born? To answer that, we've got to rewind the clock and witness the dramatic, violent life cycle of giant stars.
Okay, let's dive right in. Part 1. Birth of a magnetar, from massive star to dense core.
The birth of one of these objects happens in 3 incredibly violent stages. First, a massive star reaches the very end of its life, finally exhausting the nuclear fuel that's kept it burning bright for millions of years. Second, without that outward pressure from fusion, gravity just completely takes over. The star's outer layers are blasted into space in a brilliant, devastating explosion known as a supernova. And finally, step 3. While all those outer layers are flying outward, the star's core collapses inward under its own enormous gravity. The result? An incredibly dense, compact object left sitting right there in the cosmic rubble.
Now, this collapsed core has a specific, well-known name in astrophysics. We call it a neutron star. And this is our baseline. You see, a magnetar is actually just a very rare, highly specialized type of neutron star. All neutron stars are formed in this exact same way. They're the dense, collapsed ghosts that remain after massive stars undergo supernovas.
There's a quote that brilliantly illustrates just how absurd a neutron star's density really is. It goes, "Imagine compressing more than a sun's worth of material into an object you could drive across in a few hours." Think about that for a second. Just a tiny, spoonful-sized amount of this material would weigh billions of tons here on Earth. The gravity is incredibly strong, and matter is compressed to extraordinary, really incomprehensible densities.
But here is where the science gets truly fascinating. Because gravity isn't the neutron star's only weapon. While all neutron stars possess powerful magnetic fields, a rare few take it to an entirely different, quite frankly terrifying level. So what exactly makes a magnetar different from a regular neutron star?
Let's look at Part 2, the magnetic extreme, trillions of times stronger than Earth's. Consider the sheer contrast here. Earth's familiar magnetic field acts as a gentle, invisible shield, subtly guiding charged particles from the sun to protect our atmosphere and allow life to thrive. A magnetar's field, however, is vastly more intense, so intense, in fact, that it physically alters the fundamental behavior of matter. It doesn't just guide particles, it absolutely dominates them, reshaping the very atoms that get caught within its grip.
But this poses a slight problem for astronomers. A magnetic field isn't something we can simply see with our eyes, or even with standard optical telescopes. It's completely invisible. So how do we actually know what's out there? And perhaps more terrifyingly, what happens when this immense, unimaginable magnetic pressure reaches its absolute breaking point?
Which brings us to Part 3, Anatomy of Giant Flares, Sudden Bursts of Electromagnetic Radiation.
So while we can't see the field itself, we can absolutely detect its violent aftermath. Scientists believe that the field of a magnetar is so overwhelmingly strong that it literally pulls and twists the star's dense, solid crust. The whole star deforms under this immense tension, and eventually, that mounting stress causes a sudden, violent rearrangement of the magnetic field. It's essentially a massive starquake. The field suddenly snaps, and the result? A catastrophic burst of electromagnetic radiation that violently blasts out into the cosmos.
And here's the wild part. We've actually seen this happen. It's a genuine cosmic detective story. Back in 2004, a distant magnetar known as SGR 1806-20 experienced one of these catastrophic magnetic snaps. This enormous burst of energy traveled across the vastness of space for tens of thousands of years, and when it finally washed over our solar system, spacecraft near Earth detected an enormous gamma-ray flare. Literally for a brief fraction of a second, that distant, tiny city-sized star became one of the brightest sources of gamma rays in our entire sky.
Witnessing an event like that naturally raises a pretty chilling question, right? We're talking about sudden flares of energy that can briefly outshine entire galaxies in gamma radiation. So, with such unimaginable volatile power, could a magnetar actually destroy Earth?
Let's get into part 4, the bigger cosmic mystery, separating science from science fiction.
When assessing the real threat level, first and foremost, you have to remember that distance matters enormously. The magnetars we currently know about are many thousands of light years away from our solar system, and because radiation spreads out and weakens as it travels through the vast, empty distances of space, the energy that finally reaches us is completely harmless. So you can rest easy. There is no known magnetar currently threatening Earth. Their giant flares are simply distant reminders of just how extreme our universe can really be.
In fact, rather than a looming threat, magnetars are actually an incredible gift to science. They give researchers this amazing natural laboratory to study physics under conditions that are absolutely impossible to reproduce here on Earth. We use them to understand matter and energy at their absolute limits. Scientists are still out there trying to solve some major mysteries. How exactly do these anomalies form? Why do only some neutron stars become magnetars while others don't? And how do these immense fields evolve over thousands of years? Every new observation gives astronomers just another crucial clue.
Ultimately, a magnetar is essentially a dead star. It's the collapsed ghost of a massive sun compressed into a city-sized sphere, armed with an extraordinary magnetic field and capable of unleashing violent bursts of energy across the galaxy. It really proves one profound thing. The universe doesn't need fictional monsters. It already created magnetars.
If you could safely observe a magnetar from a spacecraft, would you do it? Tell us your answer in the comments, and subscribe to Curious Orbit for more space science and astronomy documentaries.